Today, we are diving into one of the most powerful tools in all of engineering, the state equation. It's this incredible way to take a really complex, dynamic system, like this circuit here, just buzzing with energy, and basically create a mathematical crystal ball that lets us predict its future. And you're going to see, this idea goes way beyond just electronics.
All right, so here's our plan. First, we'll get a handle on what a system's state even is. Then, we're going to roll up our sleeves and turn a real circuit into one of these state equations. We'll discover its beautiful, universal form and figure out how to actually solve it. And then, the best part, we'll see how to visualize the whole thing as a journey through space.
So, what's the big problem we're trying to solve here? Well, you've got these systems with all these different parts, and they're all interacting and changing over time. To have any hope of predicting what they'll do, we need a way to capture a perfect, complete snapshot of everything that's going on in a single instant.
I mean, really think about that. If you wanted to predict where a ball is going to land, you'd need to know its position, but you'd also need its velocity, right? Just knowing one of those isn't enough to tell you the future. It's exactly the same for these more complicated systems. Okay, so here's the formal textbook definition. The state is the absolute minimum set of variables that you need to know right now to predict the system's entire future, as long as you know what you'll be doing to it, the inputs. It really is like having the system's complete DNA at one single moment in time.
All right, that's enough theory. Let's make this real. We're going to take a simple RLC circuit, a resistor, an inductor, and a capacitor, and we're going to translate its physical reality into a mathematical one.
And we're going to do this in just 3 simple steps. First, we'll go back to the fundamental laws of circuits. Then, we'll do a little bit of algebra to focus on the things that are changing. And finally, we'll put it all together into this really neat and tidy matrix equation.
First things first, we got to go back to basics with Kirchhoff's laws. These are the rules that say energy and charge don't just disappear. Applying them to our circuit gives us our first raw equation that describes how all the parts are related to each other.
Now this is the crucial move. See, we don't just care about the state itself, we care about how the state is changing. So we rearrange the math to isolate the derivatives, the rate of change of the current, and the voltage. We're basically asking the equation, okay, how fast is my system evolving right this second?
And after we shuffle things around, we get these 2 beautifully clean equations. Each one tells us the rate of change for one of our key variables, our inductor current and our capacitor voltage, based on nothing more than the system's current state and any power we're feeding into it.
Okay, and here's the final piece of the puzzle. We take those 2 separate equations and we bundle them together into one single, powerful matrix. This is what's going to unlock all the incredible analysis and visualization that's coming up.
And there it is, the result of all that work. And what's so cool is that this isn't just an equation for our circuit. It's a universal form that can describe a huge range of linear systems, from mechanical springs and masses to, believe it or not, even economic models. This one single compact equation tells the whole story. It just says that the rate of change of the system state, that's the x dot, is determined by 2 things: the system's current state, which is the x, and any external forces acting on it, the w. So, x dot equals ax plus bw.
So let's break that down real quick. X is our state vector. That's the snapshot, right? The inductor current and capacitor voltage. X dot is how that snapshot is changing in the next instant. Now the A matrix, that's the really interesting part. It basically holds the physics of the system, how its own parts talk to each other. And finally, B and W just represent how outside forces, like our voltage source, push the system around.
Okay, awesome. We've got this beautiful equation. So, what do we do with it? How do we actually use it to see into the future? We need a way to solve for x at some future time t.
The key is this thing called the state transition matrix. But honestly, you can just think of it as a time machine. It's amazing. You give it your starting state x of 0, and you tell it how far into the future you want to go, t. It literally multiplies them together and spits out the system state at that future time. It plays the system forward for you.
So how do we build this time machine matrix? Well, there are a couple of really powerful math techniques, like using a matrix exponential or, more commonly, the Laplace transform. We're not going to get lost in the weeds with the math here, but the point is, these are well-established methods that let us calculate this matrix straight from our system's A matrix.
And this is what the complete solution looks like. Now I know that might look a little scary, but it's actually just 2 simple ideas added together. The first part is the natural response. It's what the system does all by itself, just based on its starting energy. The second part, that integral, is the forced response. That's how the system reacts to being pushed and pulled by outside forces over time.
And this is where all that math finally pays off in a big way. We are about to turn all those equations and symbols into a picture, and it's going to give us this incredible intuitive feel for how the system actually behaves.
To do this, we create something called a state space. Just imagine a graph. On one axis, we plot our inductor current. On the other, we plot our capacitor voltage. Now, any single point on this graph represents one complete snapshot of our circuit state at a single moment. So as our circuit is running, the current and voltage are changing, right? That means the point on our graph is moving. And the path it traces out over time, we call that a trajectory. It's a visual record of the system's entire journey from start to finish. Okay, now this is really cool. We can see what happens when we just change one part, the resistor. With a decent amount of resistance, the system loses energy over time, so it spirals inwards and eventually comes to rest. But watch what happens as we decrease the resistance. The spiral gets wider and wider. It takes longer for the system to settle down.
And this brings us to the grand finale. What happens if we remove the resistor completely? R equals 0. Well, now there's nothing to dissipate the energy. It's trapped. The energy just sloshes back and forth between the inductor and the capacitor forever, and our trajectory becomes a perfect, stable orbit.
And that is the whole point. That's the huge takeaway here. We took a messy physical system, we described it with some complicated equations, we organized them into one clean matrix equation, and the solution wasn't just a formula, it was a picture, a geometric journey that gives us this amazing, deep intuition for how a system really works.
So, this leaves us with a final thought, right? This technique isn't just for circuits. What if your state variables were predator and prey populations in an ecosystem, or a company's revenue and spending, or a rocket's altitude and velocity? What other complex dynamics out there in the world could we understand in a whole new way if we just saw them as a journey through a state space?